governors, throttle valve, fuel supply, prime mover, load, then feedback device to correct it. Feedback device is governor. Eta versus load. Load, eta max, optimum load. Eta versus speed, optimum speed, eta efficiency, eta versus speed omega. Intercycle between two, intracycle within. Difference between flywheel and governor. Flywheel is a reservoir of energy. It can either store or supply whenever there is either excess or deficiency of energy. Governor is a feedback device. It is mainly used to change the fuel supply whenever there is variation in load. Governor is able to do so by moving the throttle valve. Flywheel flywheel has no control on the fuel supply. Flywheel cannot change mean speed of prime mover. Governor can change the mean speed of prime mover by changing the fuel supply. Flywheel is a continuous working device. Governor is an intermittent working device. Flywheel regulates intra-cycle fluctuations. That means within the cycle. Governor regulates inter-cycle fluctuations. Flywheel is not a compulsory. Governor is a compulsory device for all prime movers. Example turbines. Governor is a compulsory device for all prime movers. Eta omega, omega optimum, eta max. Omega should be should be as minimum as possible. For same change in load, the fluctuations and speed of prime mover with governor A is smaller than that of governor B. Governor A is better than governor B. Fluctuation should be smaller. Okay. Governor, centrifugal governor, inertia governor. In centrifugal governor, pendulum type, gravity controlled, spring controlled. Pendulum type, watt governor, gravity controlled, Porter governor, and Proel governor. Spring controlled, Hartnell, Wilson, Hartner, Hartung, Pickering. Used in gramophone. Spindle, upper arm, governor bar, lower arm, sleeve, BDC, omega, engine shaft, omega, bell, MR, omega square, spindle, bell, crank lever, equal size bevel gears, velocity ratio is equal to 1, throttle valve, fuel supply. From here, fuel will be controlled. Watt governor. In watt governor, mass of sleeve is negligible. Configuration diagram HMM simple watt governor. MM if it is H open arm type watt governor. If it is like this, then crossed arm type watt governor. H is from masses to the point of intersection. H height of governor. It is distance between plane containing the governor valves to the point where upper arms are intersecting with the governor axis either by their own or when extended. Analysis of watt governor. Governor axis. This is governor axis at an angle theta. And theta is equal to R by H. This is HM. MR omega square centrifugal force will be in outside mg mass, then mg, let this be theta, tan theta is equal to id by bd, and this is I center by Kennedy's theorem. Okay, taking moment about I center, mr omega square into bd is equal to mg into id. Omega square is equal to g by r into id by bd. Omega square is equal to g by r into tan theta. Omega square into g is equal to g by r into r by h. Omega square is equal to g by h. Omega is equal to 1 by root h. Omega is equal to 2 pi n by 60. M square is equal to 895 by cap h. 895 by h. Graph of omega and h omega square is equal to g, so it will be like this. Corresponding to higher speed, the speed change in height of governor is smaller, hence the change in fuel supply will also be small. This governor doesn't work at high speed, does not work at higher speeds. The working range of watt governor is very small, 30 to 40 rpm. Porter governor, an appreciable mass was kept. Centrifugal configuration diagram. The mass here will be kept to small m is equal to mass of ball, capital M is equal to mass of sleeve or dead mass. Analysis here, then mr omega square will be like this, small mg will be like this, I will be here due to Kennedy's theorem. Then here weight will be there, mg plus or minus f by 2. Is eccentricity of lower arm, which means here from center axis to here is eccentricity of lower arm. F of friction between sleeve and spindle, tan theta is equal to id by bd, tan beta is equal to dc by bd. Mg plus, this is mg plus or minus f. Taking moments about I, mr omega square b into bd is equal to mg into id plus mg plus or minus f by 2 into ic. Solving problems using this equation is subjective. Mr omega square is equal to mg into id by bd is plus mg plus or minus f by 2 into ic by bd. Mg into tan theta plus or minus mg plus or minus f into id plus dc by bd. This can be written as tan theta plus tan beta. If we take tan theta mr omega square into tan is equal to tan theta into mg plus or minus f by 2 into 1 plus tan beta by tan theta. Mr omega square is equal to r by h into 2mg plus mg plus or minus f into 1 plus k by 2. Tan beta by tan theta is equal to k. Omega square is equal to 2mg plus capital mg plus or minus f into 1 plus k by 2mh. Special case, if tan beta is equal to tan theta, that is beta is equal to theta and k is equal to 1, lower and upper arm, both arms are of equal length, both are having same eccentricity, omega square is equal to 2mg plus capital mg plus or minus f into 1 plus 1 by 2mh is equal to mg plus capital mg plus or minus f by mh. If friction is absent, omega square is equal to small mg plus capital Mg by small mh. The omega square is equal to small m plus capital M by small m into g by h. Omega square Porter is equal to small m plus capital M by small m into omega square watt governor. Omega Porter by omega watt is equal to root of small m plus capital M by small m. Root of small m plus capital M by small m is greater than 1. Omega Porter is greater than omega watt. Governor's terminologies. Controlling force CF or F of R. It is resultant of gravity force, that is weight of sleeve and weight of balls in gravity controlled governors, and spring force in spring controlled governors, frictional force and frictional force between two different elements. F of R. It is always towards axis of rotation. That means f of r is like this, and the tendency is to reduce the reduce the radius of rotation. For an active or a working governor, f of r is greater than 0. From graph of f of r versus r, gravity controlled governor, f of r, it will be like this. The slope of f of r and r curve in at any point is equal to slope of tangent to the curve at some point. Tan theta is equal to df of r by dr. Spring control governor, it will be a straight line f of r f of r is equal to ar plus b. Slope is tan inverse a and b are constant. Centrifugal governor, fc is equal to mr omega square. It always acts away from axis of rotation. Its tendency is to increase the radius of this is another type of force. Before these two are controlling forces, this is centrifugal force. It is always acts away from axis of rotation. Its tendency is to increase radius of rotation. At equal radius, fc is equal to fr. Graph for FC versus R. FC is equal to MR omega square, tan theta is equal to tan inverse M omega square. Slope of FC and R is straight line. Tan theta is equal to FC by R is equal to M omega square. M is equal to constant. Tan theta directly proportional to omega square. Omega increases, theta increases. FC MA omega square or MR omega square. Theta is slope. Corresponding to each omega, there is unique straight line FC versus R. Theta A greater than theta B greater than theta A, omega C greater than omega B greater than omega A. Since at equilibrium FC is equal to F of R, the graphs of F of R and FC versus R will intersect at equilibrium. F of R, FC is equal to M omega square, intersect at equilibrium. F R F C R equilibrium 1, 2 points are equilibrium 2, R equilibrium 2 greater than R equilibrium 1, omega 2 is equal to omega 1 is equal to omega, not possible, which is not possible. Okay, omega 2 omega 1 is not the graph of FC versus R and F of R versus R cannot intersect at more than 1 point, since there cannot be one particular omega at two different radius. At each omega there will be unique radius of rotation. Types of equilibrium. Stable equilibrium, this is general stuff. If system returns to initial equilibrium position by its own whenever disturbed from initial position, then the system is said to be in a stable equilibrium. For example, if we move this, it will come back to equilibrium position again. Unstable equilibrium, if the system does not return to the initial equilibrium position by its own, then it is said to be unstable equilibrium. In this case, to bring the system back, work is done on the system equilibrium. Okay, neutral equilibrium, the system is always in equilibrium position. It is known as neutral equilibrium position. For the flat lying surface, then it is in neutral equilibrium. Stability analysis of grounder. Stable gravity controlled grounder. F R, this is R equilibrium, R1 R2. Mathematically, slope of F of R, mathematical condition for stable grounder, a slope of F of R versus R curve in at equilibrium position greater than slope of FC versus R straight line at equilibrium position. Okay, so df of r by dr greater than fc by r, df of r by dr greater than m omega square at equilibrium position. This is condition for stable grounder. If you like, you can observe directly. If you move from r equilibrium to r1, then here f of r is more, which means which will drive inside and decrease the radius to r equilibrium. If you move down, then okay, it will be like this. From this slope of f of r greater than, okay, df of r by dr greater than m omega square. Omega 1 greater than omega 2, omega greater than omega 2, r 1 greater than in stable governors, as omega increases, r equilibrium is increasing. Okay, r equilibrium is increasing. F of R mr omega square. Mathematical condition for unstable equilibrium. Slope of f of r versus r a curve at equilibrium position less than slope of fc versus r straight line at equilibrium position. Df of r by dr less than fc by r. Df of r by dr less than m omega square at equilibrium position. FC2, FC1, okay, F of R curve. Omega 2 greater than as in unstable governor, if omega increases, R equilibrium decreases. Spring control governor, FC is equal to MR omega square, FR is equal to AR plus B. Tan inverse slope. Unstable governor, F of R is equal to AR plus B. A greater than 0, B greater than 0, that is positive. Then tan inverse M omega square. tan inverse m omega square greater than tan inverse a. Tan inverse m omega square greater than tan inverse a for unstable governor. Stable governor tan inverse a greater than tan inverse m omega square. If f of r is equal to a r plus b and a is greater than 0 positive and b less than 0 negative, stable governor. B f is equal to ar minus b. If ar plus b uh, unstable governor, ar minus b stable governor. For active governor, f of r greater than 0, ar min minus b greater than 0, r min greater than b by a. Neutral governor, isochronous governor, f of r is equal to ar, just ar. Speed at which governor is isochronous or always in equilibrium is known as isochronous speed. Always in equilibrium is isochronous speed. Condition for isochronism: r equilibrium 1 not equal to r equilibrium 2 not equal to r equilibrium 3, but omega 1 is equal to omega 2 is equal to omega 3 is equal to isochronous is equal to constant. Practically not possible. Isochronous governor is a theoretical governor. None of prime mover require it. Between gravity controlled and spring controlled, only spring controlled governors can be isochronous. Gravity control can never be, because two lines can coincide at all points. Only one curve, one line will never coincide at all points. Working range of isochronous governor: omega max minus omega min is equal to 0 is 0. Note FR is equal to AR plus B unstable governor tan NSA F of R is equal to AR isochronous governor F of R is equal to AR minus B stable governor. An unstable governor can be converted into isochronous governor by reducing controlling force, that is spring force, in spring controlled governors. If controlled force is further reduced, the governor will become stable. Sensitivity of governors: it is the ability of governor to sense the change in output load and sense the fuel supply accordingly. Governor is said to be sensitive if there is large sleeve displacement corresponding to fractional change in load. Stability inversely proportional to sensitivity. The sensitivity of governor can be defined in following two cases. When governor is connected to prime mover, its objective is to regulate or minimize the fluctuation of prime mover. Therefore, change in fuel supply or sleeve displacement as small as possible, even if load changes from full to no load condition and vice versa. Coefficient of sensitiveness is equal to omega 1 minus omega 2 by omega min is equal to range of speed by omega mean speed is equal to 2 into omega 1 minus omega 2 by omega 1 plus omega 2. Omega 1 and omega 2 maximum and minimum speed respectively. When governor is independent to mechanism that is not connected to prime mover. At this case, governor is to be sensitive if large sleeve displacement corresponding to small fractional change in speed. Coefficient of sensitiveness is equal to mean speed by range of speed is equal to omega 1 plus omega 2 by 2 into omega 1 minus omega 2. The sensitivity of isochronous governor is infinity, since it is always an independent mechanism. If isochronous governor is connected to the prime mover, its sensitivity will be 0, that is, it will have infinitely insensitive. If it is not connected to prime mover, then infinity. If it is connected, then 0. Change in fuel supply directly proportional to sleeve displacement. Sleeve displacement directly proportional to change in height of governor. Change in height of governor directly proportional to change in radius. Change in fuel supply directly proportional to change in radius. At R is equal to RA, CF2 greater than CF1. For same change in omega, delta R1 greater than delta R2. Change in radius of governor 1 greater than change in radius of governor 2. For same change in speed of governor in which the change in radius is more, will be more sensitive, hence less stable. Between two stable governors, the governor is having which is having large controlling force will be more stable and hence less sensitive. Hunting TDC, BDC, stop us equilibrium position, hunting governor axis resonance omega is equal to omega n. Omega speed of governor, omega n natural undamped frequency or resonating speed. If the governor is stable and sensitive due to inertia, it will oscillate about mean equilibrium position with very small amplitude. If governor is infinitely sensitive, the sleeve will start to oscillate violently about extreme positions. This phenomenon is known as hunting, and it occurs when omega is equal to omega n at resonance. Stable and sensitive due to inertia, amplitude will be very small. If governor is infinitely sensitive, will start oscillating violently about extreme positions, then hunting. It occurs when omega is equal to omega n, that is at resonance. Effect of friction or insensitiveness. When the sleeve is running at equilibrium position, the friction will be zero. When the speed is increasing, the friction will act downward. F or Cf will be analogous to mg plus F, and when speed is decreasing, the friction will be upwards, and Cf will be analogous to mg minus F. Due to friction, governor will become insensitive over small range of speed. Quotient of insensitiveness is equal to omega a minus omega b by omega mg plus f mg minus f. Change in speed required to overcome friction is equal to omega a minus omega is equal to omega a minus omega b. Omega is equal to omega a plus omega b by 2. Quotient of insensitiveness is equal to 2 into omega a minus omega b by omega a plus omega b, where omega is equal to speed of governor when there is no friction between sleeve and spindle, that is corresponding to mg. Omega A is equal to speed of governor at which sleeve is about to move upwards, that is corresponding to mg plus f. Omega b is equal to speed of governor at which sleeve move upwards, that is corresponding to mg minus f. mg minus f. Governor effort, mean or average force acting on governor sleeve and responsible for its displacement. Effort is equal to F average is equal to 0 plus F by 2. Effort is equal to F by 2. If sleeve is running at equilibrium position, effort is 0. Power of governor, work done by effort is known as power of governor. Power is equal to effort into sleeve displacement is equal to F by 2 into X. These are workbook questions. Hartnell governor, R adjustable screw, P Q mg to capital MG plus Fs by 2, capital MG plus Fs by 2. Ball arm length P, sleeve arm length Q. This is sleeve arm, this is ball arm. Ball arm and sleeve arm together forms the bell crank lever, that is both welded. These are both are welded. Small m is equal to mass of ball, capital M is equal to mass of sleeve, Fs is equal to spring force. FBD at mid position. This will be mr omega square outside. C centrifugal force P Q mg plus Fs will be downward. Taking moment about point O, mr omega square into P is equal to mg plus Fs by 2 into Q. With help of adjustable screw, the spring will be always be kept in compression. Taking moment about O, if for small displacement theta 1, here also theta 1, fc into p cos theta 1 and plus mg into q is equal to mg plus fs1 by 2 into q cos theta 1. Taking theta 2, taking moment about c2 cos theta p cos theta 2 is equal to mg y2 plus mg plus fs2 by 2 into q cos theta 2. Let theta 1 and theta 2 be very small so that ball arm remains vertical and sleeve position remains horizontal. P cos theta 1 directly proportional almost equal to P cos theta 2 almost equal to P. Similarly, Q y1 y2 almost equal to 0. From equation 1 will become mg plus fs1 by fc1 into p is equal to mg plus fs1 by 2 into q. Fc2 in equation 2 will become fc2 into p equal to mg plus fs2 by 2 into q. Equation 3 by 4 fc1 by fc2 is equal to mg plus fs1 by mg plus fs2. R1 not equal to R2 but omega 1 equal to omega 2, then it is isochronous governor. So for that to be R1 by R2 is equal to mg plus fs1 by mg plus fs2. If weight of governor is neglected, if weight of sleeve itself is neglected, then R1 by R2 is equal to fs1 by fs2. fc1 into p minus fc2 into p is equal to mg plus fs1 by 2 into q minus mg plus fs2 by 2 into q. Fc1 minus fc2 into p is equal to fs1 minus fs2 by 2 into q. Fs net is equal to fs1 minus fs2. Fs net is equal to 2 into fc1 minus fc2 into p by q. Similar triangles x by q is equal to r1 minus r2 by p, where x is this displacement and this is r1 minus r2. Okay, this triangle and this triangle x by q, x by q, r is equal to r1 minus r2 by p. X is sleeve displacement, this is sleeve displacement. Fs net is equal to kx. Kx is equal to 2 into fc1 minus fc2 into p by q. K into r1 minus r2 into q by p. Q by p is equal to 2 into fc1 minus fc2 by q into p. K is equal to spring stiffness is equal to 2 into fc1 minus fc2 by r1 minus r2 into p by q whole square. P by q whole square. This is p, this is q. P by q whole square. Okay, these are the questions.